studying data structure. So before that, we were studying various tools for analyzing algorithms and designing algorithms. We began with tools like the BIGO notation and time complexity and those various notions, the various parameters with which we can analyze how good an algorithm is given to algorithms, what is which algorithm is better, and so on and so forth. Then we move on to various algorithm design techniques. We studied divide and conquer, greedy algorithms, dynamic programming. Okay. And then now we were studying data structure. Algorithm, the running time of the algorithm uh, crucially depends on what kind of data structure you use for implementing the algorithm. The same algorithm can be implemented with many data structures. We will see throughout the course, in the later part of the course also. And depending on the data structure you choose to implement an algorithm, the running time changes. Sorry, just a minute. Sorry, it's the delivery boy. That's why I need to take that call. Okay. Okay, so we are studying various data structures and we want to do a comparison like which data structure can perform which set of operations better and so on. So that depending on the algorithm, we will first analyze what kind of operations the algorithm or a particular algorithm does more frequently, so that we can choose the right data structure. There is no sort of one data structure which does which is best for all the operations. So towards that, we observed that we already knew some linear data structures, which are like arrays, linked list, and stacks and queue, and we started studying hierarchical data structure because the main motivation or one motivation is that data itself often um, displays hierarchy. For example, organizational structure, for example, file structure in an operating system, and so on. While carefully studying or observing what is a data structure, we observe that the data types are also like a data structure. It's like a data structure is like a data and an allowed set of operations, and we are sort of doing a higher and higher um, level of data structure. It's not that one the higher level data structure is better than the lower level data structure. It just means that the higher level data structures can be or is built using lower level data structures. For example, in last class only we observed that to store an arbitrary tree, the data structure that may help us is the left child right sibling interpretation. And if you really see what is this left child right sibling interpretation, it is basically among those children you you form a linked list. That's what this picture shows, and it makes sense. Linked lists are meant or designed to store a list whose size you may not know, whose size can be too small also, too large also. And if you carefully understand, that was the reason of, or one of the prime reason why we studied linked list and not arrays. The array had this difficulty. It's a static. The size you have to sort of define at the definition or of the array. But if the linked list is flexible, and this is the exact property of linked list we had exploited in the left child right sibling interpretation. The name only is from the semantics of this linked list. This left child and right sibling. So this is what I mean by building higher level data structures using smaller level data structures. But it should not be taken or understood that higher level data structures are like they are better, and it is always better to use some higher level data structure. It's not like that. We also observed that the basic operations like insert, delete, and search, and we wrote down their time complexities. And yesterday only we observed that although the special binary search tree, whatever the reason may be why it is special, although this performs all these three operations in order log n time, uses extra space operation. The extra space. What is extra space? Space other than the data. Uh, so that extra space, we will see that for linked list also it is order n, but for arrays it is order 1. You just store the start of the array. So you should not you should always carefully compare or given any two data structure. It is always a good exercise to think of a scenario where the first data structure is more appropriate, more suitable than the second one, and also think of another application, another scenario where the second data structure is more suitable than the first data structure. Okay. uh, okay. So then we defined what is called rooted tree, and the strange notion that for some reason computer scientists believe that root are at the top, and trees grow top to bottom. We define tree recursively, and from the definition itself, some easy but important observations we made. For example, tree is connected. The number of edges is n minus 1. We defined various terminologies in the context of tree, for example, parent, child, sibling, and so on. Then we saw the left child, right sibling representation to represent a tree. Then we move on to a special kind of tree, which we call binary search tree, and these sort of trees are suited for the search operation, and we'll see insert and delete operations also. And why is it the name is binary search tree? Because every node can have at most two children. That's it. And search is that data cannot be stored arbitrarily. There is a rule, and it's like that at every node, the data stored at that node should be less than the data stored in its right subtree, and it should be more than the data stored in its left subtree. Okay, and using this, we observed that this is a binary search tree, and we also studied insert operation, and we demonstrated how, because of this property of how the data can be stored, data cannot be stored arbitrarily or haphazardly. Because of this property, insert operation has become very easy. Not only insert, but also search is very easy. And the time complexity of insert and search is both order length of a longest path to a node or to a leaf node. In the worst case, the number of steps will be the length of the path from root to any node. Okay, so that's where we stopped yesterday. Questions, if you have any. Okay, so now let us resume where we stopped. Let me begin with defining few more notions in the context of binary search tree. These notions are defined with respect to any trees also. When we say a length of a path, what do we mean by a length of a path? It is the number of edges involved. It is not the number of nodes. For example, the length of the path from 200 to 400 is 3. This is just a convention, and if we follow this convention, the length of a path from 200 to itself is 0, which is just a convenient convention. That's why we define the length of a path to be the number of edges, not as the number of vertices. Then we define something called height or depth of a node, and it is the length of the root to node path. In every tree, for any node, there is a unique root to that node path, and its length is, we call it the depth or height of that node. For example, can someone tell me what is the depth of node 250? Akshay Mandal, can you tell me what is the depth of node 250?
So 3.
Okay, what is the path from 200 to 250? Can you tell me the path?
So 200 to 300 to 250.
Correct, here is the path. What is the length of this path? How do we define the length of a path?
Mm.
It is just written in the first line of this
The number of edges.
pages. So can you now tell me what is the
The
depth of?
2.
Very good. Why the attendance is too low? By the way, please take the attendance, Debabrita. But why any feedback is how are we doing as a teacher? Any feedback? Why attendance is so low? Any clue or any suggestion regarding teaching? How can we improve our delivery of content or anything? Yeah, I'm really curious to know why attendance is so low. Anyone can have any insight or any idea why attendance is?
Sir, from 12 o'clock we have a maths exam, so that can be the reason.
Oh, okay. Okay. By the way, so feel free if you have any feedback, any suggestion regarding the course delivery, the way we are teaching, feel free to drop an email to PPC and me, and we are always encourage you to do that. So we really appreciate those sort of inputs. Okay. Continuing. So similarly, the depth of the node 400 is 3, because the root is 200, root to 400 path has 3 edges. The depth of a tree is the maximum depth of any node. For example, the depth of node 100 is 1, depth of node 250 is 2, depth of node 200 is 0, depth of node 400 is 3. We take the maximum depth, and that is the depth of the tree. So the depth of the tree is 3 in this example. So we now formally or succinctly write that the insertion that we discussed yesterday takes big O of depth of the binary search tree time. Okay, and not only insertion, the search also. Search also takes the same amount of time, and we will see that the deletion will also take the same amount of time. So all the time required for the 3 basic operations of search, insert, and delete, they crucially depend on the depth of the tree. Okay. But before discussing deletion, let me discuss another important operation, which are traversals. So what is the job? The job is to list down all the nodes in the tree. Now, for arrays and linked lists, because those data structures are linear, this job was sort of trivial, and we did not highlight, okay, do a traversal or something like that, because you just start. For linked list, we are anyway storing the head of the linked list, the starting node of the linked list, its address, and you can just follow. Array also same thing, but the tree is a hierarchical data structure. So there are various ways of how you can list down the all the nodes, and all have very important applications. All are very important. So let me discuss that. First is pre-order. Pre-order is you you are at a node, say X. So you visit node, visit, let me write this way, visit current node. That means where you are right now. For example, in the beginning, uh, you are at the root. So by storing tree, we store only the pointer to the root node. So you are at the root. So first is visit the current node. For example, suppose you are traversing, that means you are sort of enumerating. Now, if you are supposed to print all the data, so visit current node means that the print the data in the current node. Then you go to visit left subtree. We'll see. And then once you finish left subtree, then you visit right subtree. Okay. Next is in order traversal. It's the same, these three things. So it's depending on when I visit the current node, the name comes. For example, here we are visiting the current node at the beginning. So we call it pre-order. We are visiting before we visit the left or right subtree. Now, how does the in order will be? The in order is like you put the current node in between left visiting left subtree and visiting right subtree. That is in order. So you always visit left subtree before you visit right subtree. But depending on when you visit the current node, you have different traversals. So now can someone help me? What should be the post order?
Left, right, root.
Left.
Left, right, current node. Is it very easy? Let me highlight that. Okay, so now let's enough definition. Let's see this in this example. Let me catch this example and let's do these three traversals for this BST. Okay. First we do, let's say, pre-order traversal. We are at the root node, and by definition, we should visit the current node. Say, when we visit, we will print that. That's the task at hand. So we should perform the task at the current node first, 200. Then I move on to, let me make it slightly more non-trivial. Move on to left subtree. Left subtree means what? Left subtree means I go and apply the same principle of pre-order traversal on the left subtree. Forget everything else. Just do a pre-order traversal on the left subtree. That is what I have enclosed in that by this dotted line. And how? Again, same principle. So think of now you are doing a pre-order traversal on the left subtree and alone. That's it. So again, what should I print then? I should visit the current node. Current node is 100. Then I visit the left and there is nothing in the left. I don't have anything to do. Then I visit right, which is 150. This finishes the pre-order traversal of the left subtree of 200. Now what I am supposed to do? I am supposed to do a pre-order traversal on the right subtree and apply the same principle. Now when I go to right subtree, I am at 300. So I visit 300 first. That's what pre-order mandates me to do. Then from 300, I am supposed to print the left subtree, which is 250. That finishes the left subtree of 300. Then I go to the right subtree and I am at 350. I print 350. Then I am supposed to visit the left subtree of 350, which is empty. And I go to the right subtree of 350, which is 400. Is this clear to everyone? Jogu Bhanuteja, can you please help me with the in-order traversal? Jogu Bhanuteja, please unmute. Lathia Deep Mahendra Bhai.
Yes, sir.
Yes, can you tell me what should I write first in the pre-order in-order traversal?
Hello, sir. Am I audible?
Yes, you are audible. Can you hear me?
Yes, sir.
Yes, can you please tell me with this in order, what should I write first?
Sir, 100.
100, very good. Then
150.
150, very good. Then
200.
very good, you stopped. Please mute
Okay,
yourself.
sir. Okay, thank you, sir.
Mihir Raj,
Yes, sir.
what should I
Sir,
write?
after that we should write 250,
250,
300,
300,
then 350,
350, 400.
and
Thank
then
you.
400.
Thank you. Sanket Sachin Jet, please help me with post order.
Yes, sir. So first we visit the left subtree. So we will go to 100 and 150. Then we visit the right. So if we would start with 150.
Yes, very good. 150.
Then go to 100.
Very good.
Then go to 200.
Shall I write 200?
Like we will visit the right subtree then.
Yes. And you tell me what should I write?
Sir, 250.
250, very good. You please mute yourself. Thank you. Somebody. GVK Sai Sarath. GVK Sai Sarath. Dhanraj Kumar.
Yes, sir.
Yes, can you please help me? What should I write after 250?
Yes, sir. 400,
400,
350,
350,
300,
300.
200.
200. Very good. Thank you. Very good. Thank you. So I hope traversals are clear. If you have any question regarding these three kind of traversals, there are of course other kind of traversals like level order traversals where you traverse level by level, but these three are the most important. And I hope these three are clear. If you have any question, please please unmute yourself and ask. Okay, so there is no question. So let's move on to deletion. We had studied insertion, search, and let's study deletion. How will I delete various nodes? Again, like insertion, let me show the principle or algorithm using an example. Okay. So let me delete, or let me enlarge it slightly a bit also. Maybe 150. Not 150. 90. 70. I hope I'll be able to make my point. Okay. So let's delete the. Which should I delete? Let me delete minus say 260. First, like insertion, I need to search or go to the node where it is. If it is not so, the first thing is search for the node. You are at the root node and you search for 260. I'm at 200. 260 is more than 200. If 260 is present in that tree, it can only be present on the right subtree. So I go to right. I go here, and then I come to 300. If 260 is present, it can only be to the left subtree. I come at 250. If 260 is there, it can be only on the right subtree. I come at 270. And again, if 260 is there, it can only be in the left. I come at 260 and I discover 260. Can someone tell me how can I delete? Feel free to unmute and answer. How can I delete 260 without violating EST property?
Remove the 260.
Exactly.
Just remove
This is
it.
the easiest case. When the node you need to delete is a leaf node, it is just drop it. That's it. You don't have anything to do. So simple case, simple, very easy. That's why this is the first case. When the node you are deleting is a leaf node, it has zero children, then you simply delete it. That's it. Nothing will be violated. So let me delete 260. Good. So we know how to delete leaf nodes. So let me write here also what we are doing to keep track of it. So first case is leaf. Leaf node is just drop, just delete. That's it. Second case is the node you need to delete has degree 1. It has one child. Then how can you delete it? You cannot simply drop it. Who will be the parent of that new child? Let's see. So let me try to delete, say 100 minus 100. So again, as usual, start at root node 200, and if 100 can be present, it can only be in the left subtree, and I come and reach 100. Can someone help me? How can I delete 100?
We store the address of the child of 100 and we just
Yes,
remove it and connect.
and then I stored the address of the child of 100, which is the address of 90.
So, and we simply connect 90 to the
Yes.
parent of the node we're deleting, which is
Correct.
200 in this case.
Both you are correct. I think Arup you was in this direction. But if you delete 100, what will happen? The problem is that 90 does not have any parent. 90 has lost his parent. 200 has lost his one child. So I don't merge them. That's it. So let me again do the copy. This is the only time I enjoy teaching using iPad. Then yeah, physical board. I can easily copy. Yeah. So what you do is you simply delete it. Okay. So this is also easy. Let me not write it. It is, you have understood. If it has one child, make that child attached to its parent. That's it. Okay. So everyone has any doubt of how we can delete the case when the node has one child? Shall I do another example? Shall I show again by deleting say 90 or 350 or 270? Please don't be shy. You're spending your time.
Yes, another example would be good.
Good. I want this. So let me delete 350. Minus 350. Has also one child. See, the case we are doing is that when a node has only one child. Duplicate. So how should we do? Again, if I so for the if it was a leaf node, I can simply drop it. Why I can't drop when a node has only one child? Why I can't simply delete it? Because it has a child node. So the idea is that you make that child node attached to its parent. So you delete 350 and make the child node attached to its parent. The parent of 350 was 300 and the child of 350 was 400. You make 400 a child of 350. It is always possible because the parent of 350, because 350 is deleted, the parent has now one child slot left where the child of 350 can always get attached. Yes, so is this clear? Okay. Now, so let me not verbosely write it. I think let me write understood. So the third case is when the node that I want to delete has two children. So for example, what should I delete? Let me delete 300. So let's delete 300. Can someone help me? How should I delete 300?
You can replace 300 and 400 and just delete the leaf node.
Okay. But if I exchange 300 and 400, then BST property is violated, right?
I mean, 400 will be always bigger than 200, and the number to the left of 200 will always smaller than 400.
So I should exchange what to 400 and what 300.
300. Yeah, and then we just remove the 300, which will be the leaf node.
Correct. Let me make this a little more interesting. You're right, but let's add some more fun. It was too easy. Let's make it a bit complicated. Yes. How can I delete 300?
Exchange it with 350. 300 and 350.
Exchange with 350. Correct. So what is the principle? Who told the answer?
We're trying to.
Arup, yeah.
We are trying to find the the supposition, the next number which can be will be fit for that position which we are trying.
Excellent, excellent. First is that, you know, these the two easy cases we have discussed. Let me explain what he meant. The easy cases are when the node I am deleting is a leaf node and one child node, or it has one child. So the idea is we will somehow rearrange the tree, do slight modification in the tree, so that we are in the first two cases. Again, slowly, if the node I need to delete has two children, then I will sort of rearrange the tree so that now in the new rearranged tree, the node that I need to delete is like one of the two cases. It has either a leaf node or a one child. And the way to do it is there are two options. So one option is that you look at the right subtree and see what is the minimum value, because you know at the end 300 won't be there. $300 won't be there. So 300 is like 300 is gone. So let me find a placeholder for 300. There is one placeholder who can perform the job of 300 is the minimum value in the right subtree. So if I delete 300 and instead of 300 I put 350 here, of course I delete 350 also here. That means in some sense move 350 to in the place of 300, then the BST properties is maintained, because 350 is the smallest value in the right subtree, and that 350 I am putting it in the place of 300. So the right subtree is now the values there are more than 350. Why? Because 350 was the smallest value in the right subtree. The left subtree is always fine because 350 was a value in the right subtree, and any value in the right subtree is more than any value in the left subtree. So BST property is retained. So what is the algorithm? If you need to delete a node which has two children, sort of delete that node and also find the smallest node in the right subtree and put that smallest node in the place of deleted node. Again, if you are in a position where you need to delete a node who has two children, one option is that you delete that node, but you will put some other node in that place, exact same place. Which node? The smallest node in the right subtree. And it is easy to see, or if you just calmly see, then you'll see that BST property is maintained by putting the smallest value in that deleted node. There is another option, another equivalent mirror image option. Instead of putting the smallest value in the right subtree, you put the largest value in the left subtree, and the same thing happens. Okay. Now let me make it slightly more tricky, in the sense that, let me write it, 200, 90, 70. Because here this was 350 was a leaf node, you can simply delete it. But 350 may not be a leaf node, no? Can you see the problem? 350 may be, what will happen if 350 also had 2 children?
So 350 cannot have 2 children.
Excellent, very good. Very good. 350 cannot have 2 children because, again, yes, you please explain why 350 cannot have 2 children.
So because if 350 has 2 children, then the left child of 350 automatically becomes the smallest element in the right subtree.
Very good, very good. Look at the left child of 350. That is less than the 350. How can then 350 be the smallest element in the right in that subtree? So 350 cannot have 2 children. Can 350 have 1 children?
Yes, sir.
350 can have 1 children, and we'll see that case. 270. $290. $400, $450. Okay. So let me again delete 350, and let's see how we will tackle it. So 350 is gone. By our algorithm, our strategy, we will find the smallest element in the right subtree, which is 400. Now I cannot sort of simply delete 400 and write 400 in place of 350, because 400 has one child, namely 450. Then how should we do? Is the case clear? The smallest element in the right subtree, if it is leaf, you can simply delete it and copy that data to the deleted node. But if it has only one child, which can be the case, here is an example of the case. How will you delete 350 then?
Will just store the address of 450.
No, what is the strategy I'm saying? You can make this.
And first exchange the value of 400 and 350, and then from 350 we store the value of 450, and then after deleting 350 we just connect 450 to 400.
Excellent. So here is the idea. The idea is that you sort of first of all write 400 here. So that's the right placeholder. Now the problem is that I have this node here, and I don't know how to use this. And I would have been happy if this node was not there. Delete this node. We know how to delete a node which has only one child. That case we have already covered. And so delete this node. And how will you delete the node? Delete the node which has only one child? By bypassing. You to delete it and make the parent, make the child attached to its parent. The way we handled the case when we need to delete delete a node which has one child. The same idea. So let me summarize. There can be three cases for deleting a node. If it is leaf node, simplest, just delete it. Nothing will go wrong. If it has one child, you delete that node, and where we are doing here. If it has only one child, you delete that node, and because it has only one child, make that child attached to its parent. For example, we have deleted 100, and we have made the child of 100, which is 90, attached to its parent, which is 200. That is how we handle one child case. It is also very easy. And the trickier, slightly more interesting and non-trivial case is when the node to be deleted has two children. And when it has two children, we have two strategies. Just stick to one. Both are equivalent. Both are perfectly fine strategy, not equivalent. So you sort of delete that node and find out the smallest element in the right subtree. Now you move that smallest element to the position of the deleted node, and then you delete the smallest element. It's like you delete the node 350 after shifting 350 to in the place of 300. Now if 350 is a leaf node, then you simply delete it. If 350 has one child, it cannot have two child. If it has one child, then you delete how you deleted or handled the case when a node to be deleted has one child. Is this clear to everyone? Let me do another example. Let me delete another one. So that it becomes crystal clear to everybody. $400, $450, $250, $200, $270, $290. Okay, now let me delete what? Let me delete 200. Root node. Let me delete the root node. Let's see who can help me. Lavinder Kaur.
Yes, sir.
Yes. Can you please tell me how will I delete 200?
Sir, replace it by 200 in the right subtree.
This is 220. Yes, thank you. Yeah. So you just delete 200 and find the smallest element in the right subtree, which is 220. You write 220, you the place of 200, and just delete 220 because this is a leaf node. You just delete it. That's it. In the next iteration, if you want to delete 220, you delete 220 and write 250 in the place. Simply delete how you would have deleted 250. It has only one child. Okay. Anyone want me to do another example of deletion? Is this clear to everyone? Please feel free to unmute and tell me. Yes, another example will help. Yeah.
So can we go back to the initial example before we deleted 350? I have a question related to a case.
Yes, here.
Yes, sir. So supposing we remove the node 290 and instead we have a left node 260.
I move. So let me write here. Or let me write with another color. So in which tree? In this tree with 300 there, 300 and 350 there. Shall I edit?
Yes, sir. Yes, sir.
Okay. Now you tell me what should I do?
So we remove the right node 290 present in the left subtree, and instead we place a left node at 270 with a value of 260.
Okay.
And so now using the other option that we had of replacing by the largest value in the left subtree, I want to replace 300 with 270.
Okay, you replace. And
Yes,
then
sir, but then
make
what you...
this a child of this.
Okay.
You know, you are removing 270. 270 has one child.
Yes.
And it is a some child, left child or right child of its parent. So if you remove 270, one slot is freed up. In that freed up slot, you attach the child of 270.
Okay, sir. Okay, sir.
260
Yes,
or
now I
a
understand.
right child of 250. But that's a good question. Same thing you need to do it here. For example, let me write. I think that's a good question, and let me elaborate this with this example also. 220, 90, 70, then it is 400, 450, then it is 250, 270, 290. Now you delete again what? Delete to 220. You delete 220. You should write 250 there. And now you need to delete 250. How will you delete? You delete it, and the child, which is 270, make it attached to its parent. In this case, 270 will be the left child of 400. Okay, so the resulting tree will be 250, 90, 70, 400, 450, 270, 290. Is this clear to everyone? Please don't be shy.
Yes.
And unmute and tell me if you want me to do another division. Please don't be shy. That is deletion. Okay. So what is the time complexity? Time complexity is, you are basically traversing the tree, and the maximum that you traverse is till the depth of the tree. Either the first step is searching. When you are searching, the node to be deleted could be an intermediate node or it could be a leaf node. Now, if it is a leaf node, it is you delete that, and in that case, the time complexity is order depth. If it is an intermediate node, then you are supposed to find a minimum element in the right subtree, and that is again like I let you do this as a homework, that finding a minimum in a left right subtree also takes depth of order depth in the right subtree. For example, so suppose here is a tree and you want to delete it, and first step is search. You start from root, and suppose here you find the node which needs to be deleted. Now, if it is a leaf node, then you simply delete it. If it is on exactly one child, then you don't have to traverse this path more. You just see who is the one child and make just simple pointer manipulation, pointer rearrangement, make the left child of parent to point to this bypassing. That's it, and then delete it. Isn't it? So again, the time complexity again is order depth of the tree. On the other hand, if it is if this node has 2 children, then what you are supposed to do? You are supposed to find a minimum element in the left subtree, which is again like traversing a path. And when you find a minimum node, suppose here is the minimum node, use some other color. What you do? You copy, so you copy this data here, and then you delete this node. Now deleting this node, it is again, it's just simple pointer manipulation. That means what? That means you make the child point to its parent. So what I am saying is that this pointer manipulation is like updating 1, 2, 3 pointers. So it takes order 1 time, and the most of the time is spent traversing the path, and so the time complexity of deletion is again order depth. Depth of the tree. Yes, is this clear? The time complexity is order depth. Oh, good. But
Yes, sir.
how
So-
bad that? Yes. Yes, please.
So I just had one doubt. A child does not have access to the pointer to its parent. So once we reach the bottom of the tree, how is it that we'll be able to point to the other pointer? That is, do we constantly have to have the values present that, okay, if we reach the depth, we will be updating it?
Correct. So that's a good question, important question, but that is implementation details. You know, one way to handle this is, or cleanest is, to store the parent pointer also in every node. Other than data, left child and right child, you store the parent pointer also. That is one way. Another way is that, you know, it's like always you only have to keep track of a node and its child. So before leaving the node, you ensure that you do not need that node again. For example, when you are finding, or when you are finding you are searching a smallest element in a binary search tree, which you need to do while you are deleting a node which has 2 children, you are searching for a node which does not have left child. And you need to sort of, in case of deletion, you need to change its parent pointer also. Why don't you? So when you are at this node, you check whether it has a left child. First of all, if it has left child, then only you come to this node. Otherwise, you don't come. And if it has a left child, you check, does this left child has a left child, or it is empty? If it is empty, if it has a left child, then only you forget the current node and come here. And then again do the same thing. If you see that, so this is x, this is y. If you see that when you are at x, you see that y does not have a left child, then you have found the smallest element y, and you know what to do. If you want to delete y, you need to see the right child and make the left child pointer to point to the right child of y. This task you perform while you are at x. Because if you leave x, if you forget x and come to y, then you cannot do that unless you have parent pointer. So these are the 2 approaches. It is important question, but these are implementation details, and both ways you can implement. But this is a good question, good and important question. Good. Now let me ask, but how bad the depth is? For example, if my tree stores n nodes, what will be the depth of the tree? Can the depth be as bad as, say, n-1 or n, like order n? Can the depth be order n?
So it can be at max n, so yeah, order n.
Order n. Anyone else who thinks it cannot be order n? It's like a tree, no? You know, there are so many branches. Anyone else?
Sir, it should be login.
It will be like login. It looks like login, right? And which is true in some sense that in Thursday's exercise we'll do that if a BST is randomly built, like then we expect the depth of the binary search tree to be roughly like login. We'll prove this in Thursday's tutorial. But we are talking about worst case, how bad it can be. Anyone?
N, it can go N.
I have a question.
Yes, just hold on a second. Yeah, just hold on. No, don't forget your question. Anyone who feel
It
that
can be N. I mean, it's a skew tree. All the elements are on the right side. That's all.
correct. Yes, Ishan, please go ahead with your question.
So, how can an average case be as good as the best case if there is a good enough possibility of having worst cases? You said that on an average we would expect a random BST to have depth of log n, but so there are a lot more permutations where the depth will be of the order n. Like this is an order n, the one which you've currently drawn, but I can easily draw n minus 1 depth BSTs.
Correct.
So,
what is the time complexity of quicksort in worst case? You know quicksort, right? Do you know quicksort? Anyone?
Order n square.
Order n square, correct. How many of you know quicksort? Just raise your hand. Everyone knows quicksort. It is taught in PDS class, right? Everyone knows quicksort. Yes. So order n square. What is the average case of quicksort? Please unmute and
Sir, n log n.
N log n. What is the best case of quicksort? It is also n log n.
yes, sir.
So apply Ishan, apply your logic to, because this logic, the quicksort example shows that it is wrong, but don't be disheartened. Carefully follow your logic and find out where and why it is wrong. And of course, in Thursday's tutorial, we will prove that the average depth is order log n. We'll see a concrete proof. So we see that the depth can be, in the worst case, it can be as bad as order n. So next, what we will do is that we will study special binary search tree, a binary search tree with some more property than binary search tree, which ensures that in worst case also the depth is not n, the depth will be like order log n. Okay, so before doing that, let's take a 5 minutes break. It's 11:04 in my iPad, so let's come back at 11:10. 6 minutes. Okay. So in rest of today's lecture, we will see another special kind of binary search tree, and there are various ones. Means the one we will study is AVL tree. The name it is named after the inventors Adelson, Velsky, and Landis. But it is not the only special kind of binary search tree. There are many special kind of binary search trees, and on a high level they're pretty similar, like they all are designed to ensure that the depth of the tree is order log n, and in some sense at the end of the class I'll comment, it's like they are all like in spirit they are similar. It's like they 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 achieve the same task slightly differently. Okay, so if we ensure that the depth of the tree is order log n, then it sort of not immediately imply that search, insert, and delete can take order log n time. Why it does not immediately imply? Can someone tell me? Suppose I define a binary search tree with some other extra property, which ensures that the depth of the tree is order log n. I say that I cannot conclude immediately from this fact, combining with the fact that search, insert, and delete in binary search tree takes order log n time, I cannot combine these two facts and conclude that that search, insert, and delete also takes order log n time. Why I cannot combine these two facts? Anyone? This is a subtle question. If it is, I'll let you think. If you do not find the answer, yes, please.
You're just asking how whether or not the second statement is a direct implication of the first statement.
First statement and the fact that for binary search tree, the search, insert, and delete takes order depth time. AVL tree is a binary search tree with some extra property. Every AVL tree is also a binary search tree with some extra property, and those extra properties ensure that the depth of the tree is order log n. So let's use that fact that AVL tree is a special kind of binary search tree, and its depth is always order log n. That's fact number one. Second fact is in search, insert, and delete takes order log n time for binary search tree. My question, although I have written that implied that search, insert, and delete takes order log n time, is wrong. There is some subtlety due to which I cannot write that these two statements, these two facts combined, I can conclude that this sort of special kind of binary search tree, which I am calling it AVL tree, which I am yet to define. But it takes order log n time for search, insert, and delete. I'll let you think. So there is a subtle reason why I cannot write it. So let me write a question mark here. Okay, good. Now let's ask why a binary search tree becomes skewed. So one sort of reason is that there are many nodes where left subtree is heavier than the right subtree. That's the reason, right? That's what we mean by skewness. One subtree is much higher, heavier than the other subtree. So if you want to ensure non-skewness, then what will be the first property that, okay, so let's ensure the property that at every node, the left subtree and right subtree should have the same depth. So option 1. Let us define a special binary search tree, which is a binary search tree with the extra property that the left subtree and right subtree at every node have the same depth. Is it a how good is this sort of special binary search tree? Feel free to unmute and speak. For example, will it ensure that the depth of the tree is order log n?
So I think yes.
Yes, obviously. If every node at every node, if the height of depth of left subtree and depth of right subtree is same, then the height then the depth of the entire tree must be order log n. So is it a great option?
It will have a compulsion that number of nodes will be 2 to the power something.
Or what do you?
Yes, sir. So because
Yes. So it's like too rigid a condition. We can have, for example, I cannot have any special kind of binary search tree with two nodes. If I have exactly two nodes, n equal to 2, there is no binary search tree which satisfies this property. Do you see? One must be root node and the other node must be the left child or right child. I cannot ensure that this if I make it left child, then then left subtree has more depth, so on. So it's too rigid, not very useful. So the problem is that the number of nodes must be 2 to the power n minus 1. Then only such trees exist. Otherwise, otherwise for other values of n, there is no such tree, which there is no binary search tree which satisfies this property. So that way it is useless. Okay. So option 2, let's relax this slightly. And that is, let me write, that is the AVL tree condition. AVL tree property. The depth of left and right subtrees can differ by at most 1. Claim the depth of AVL tree is order log n. If it has n node, the depth is order log n. Is it easy to see? Okay, don't worry if it is not easy to see. It is not easy to see to me either, and that's why I will prove it. But let me defer this proof either to tutorial or at the end of this class, and let's feel the tree. Let's feel our AVL tree. How we insert. Search is same. Search is same because search does not modify the tree. But insert, we'll see insert modifies the tree, and if we modify the tree, we always have the fear that this AVL tree property may get violated at some node. So if I am inserting a node in an AVL tree, after insertion, if I simply do a binary search tree insertion, then what is the guarantee that in the resulting tree the AVL tree property is still valid. That's where the non-triviality is, that I need to again make some changes after inserting so that the AVL tree property, if it was violated, is restored. Is everyone with me? So you're doing insertion. Why? The search is plain old binary search tree search. We do not need to do anything. Why? Because search does not modify the tree. So if the AVL tree property was holding before, after search also the AVL tree property holds. But for insertion, there is a danger that it may get violated. No AVL tree property. And the idea is that the high level algorithm is that you first insert as a binary search tree insertion, and then check if there is a violation in the node, a violation in any node. Well, the violation could be only of the AVL tree property, the extra property, the extra balance condition. Okay, and if there is a violation, make suitable changes. That's the high level idea. So it's a two-step algorithm. Insertion and delete both is a two-step algorithm. Insertion is, first step is do the plain old binary search tree insertion. Second step, you see if there is a node where AVL tree property, the balance condition is violated. If the balance condition is violated at any node, you make suitable changes. The second step. Everyone with me? Okay. So again, let's see this with an example. With a sequence of insert. So initially I have an empty AVL tree. I insert one. I have a single node. It's fine. AVL tree property condition is satisfied. Let me insert two. Still fine. Let me insert three. Aha. Now, can you see the AVL tree condition, balance condition is violated? Can someone tell me where the balance condition is violated?
At 1.
At 1. Very good. At 1 in this node. Okay. So the left subtree has depth 1. On the other hand, the right subtree have depth -1. Let's define the depth of an empty tree to be -1 so that it is consistent with our definition, like the depth of a singleton node is 0. So that way it is violated. What do we do? The fundamental operation is what is called rotation. So let me explain rotation. Whenever there is a violated node, the balance condition is violated, we will apply rotation. So what is rotation? And this rotation is the operation which sort of common to all other kind of special balanced binary search trees. These are called balanced binary search trees. AVL tree is one type of balanced binary search tree. Red-black tree is another balanced binary search tree. There are many other trees or binary search trees also which are balanced. It is like binary search tree with some extra property which ensures that the tree is sufficiently balanced so that the depth is order log n. And the insertion and deletion subroutines in all those balanced binary search trees, the first step is same. That you first do the plain old binary search tree insertion, mostly, or at least the ones I am aware of. And the second step is that if there is a violation, you apply rotation. Now, how will you do rotation and where and so on? This can differ, but the same rotation operation is used to restore the balance property. So that way, this rotation operation is also very fundamental to all binary search trees. So let's see what is rotation. So suppose here is a key K2. First, I'm defining rotation. And then I will apply this in this example. This is a subtree. Let's call it Z. K2 has a child K1. And it has a subtree. Let's call it X. left subtree and right subtree. X, Y, and Z, they can be empty also. Now, a right rotation with respect to K2. So with respect to K2, I am rotating right. By that, I mean that you change this to this tree. Make it K1. As if like it's like rotation. You are rotating, so K1 has gone to K2's place. K2 has come down. Now let's see where we attach these trees X, Y, and Z. Z, the only place it can get attached is the right subtree of K2. There is no other option. The only place where X can get attached. Where can X get attached? The keys, the values in X is less than K1. The only option for this subtree X is the left subtree of K1. And where can Y be attached? Y was the right subtree of K1, but now K2 has taken the place of right child. Where can K1 Y can be attached? Can be attached in the as a left subtree of K2. Does it maintain the binary search tree property? All the values in Y were less than K2. So if all the values of Y are less than K2, then the binary search tree property is maintained at the node K2. All the values in Y were more than K1. So at the node K1 also, the binary search tree property remains intact. Everyone with me? Is it clear to everyone that the binary search tree property is maintained after rotation also? So let me write these two properties. BST property is maintained. And the second important thing is that how much time the rotation takes. If you see, it is just updating few pointers. For example, you need to update the right child of K2 and the left child of K1. That's it, no? And if there is a parent of K2, then that also needs to be updated. So at max 3 pointer variables needs to be updated. That is what rotation is. So takes big O of one time. Everyone with me? Rotation, these called left to right rotation. If symmetrically, you can also think of right to left rotation. So a rotation takes order one time because it only needs to update 3 pointer variables. If there is a parent of K2, that parent's child node needs to be updated because now it should point to K1. The right child of K1 should be updated. It should point to K2 now. And the left child of K2 should be updated. It should point to Y now. So updating 3 pointers at 2 or 3 pointers. If K2 is the root of the tree, then only 2 pointers needs to be updated. That's what rotation is. Is everyone clear with this definition of rotation? We'll see this example and how this transforms. So let's make this transformation. The right child at 1 is heavy in this example. Now let's come back to this example. Right subtree is heavy, so I should rotate from right to left. From heavier stuff to the, I should move some stuff from heavy part to the lightweight part. So if I move, so this becomes 2, 1, 3. Everyone with me? Please unmute and ask or tell me if something is not clear. Please do not wait for me to to request you to unmute and thing. Now let's continue. Let's insert 4. 1, 2, 3 we have inserted. Let's insert 4. Everything good so far? At 3 it is fine. At 2 is also it is fine. The balance property is fine. Let's insert 5. Now there are 2 violations. One is at 2, another is at 3. The algorithm is you should rectify the violations bottom up. So after inserting 5, you traverse the path from 5 to leaf node and check where is the first violation. So at 3 it is there is the first violation. First take care of the violation at 3 by doing appropriate rotation. How should we rotate? Left rotate or right rotate? I should rotate with respect to 3, but right to left, because right is heavy and left is light. So let's see, 2, 1, 4, 3, 5. Now it looks like a magic that in the process of fixing the balance condition at node 3, the balance condition at node 2 is also. What I claim is that it's not a magic. It does not matter how many nodes along the leaf to root path, or not leaf, it's a newly inserted node. Yeah, it will be a leaf to root path. It does not matter how many violations are there. If you fix the first violation, first means when you are going from leaf to root, the first violation you fix, all the subsequent violations will be automatically fixed, which is not easy to see, or may not be easy to see, but you can think about it. Why? I'll not prove it, and not part of syllabus also. But that's it. So you just need to do one rotation in insert. Is this clear to everyone? Ashish Kumar Shah. Ashish Kumar Shah. Bhagyoshri Sharma. TS, please note down the names who are not responding. Bhagyoshri Sharma. Am I audible? I'm audible, right?
Yes, sir.
Okay.
Yes, sir.
Okay. Divyanshu Mittal. TS, please note down the names who are not responding. Divyanshu Mittal. Please raise your hand if you are awake or you are listening. Please raise your hand. Okay, keep the hand raised for some time. It takes some time. Okay, among the raised hand, let me ask Rajdeep Das.
Sir.
Yes, help me. So let me insert 6. Now, can you tell me, is the balance property is violated?
Sir, it is violated at 2.
2, very good. Now I want to I do what kind of rotation? Left rotation or right rotation? Left to right or right?
Sir, the right part is heavy, so right to left.
Correct, very good. Now can you tell me what should be how should the new tree look like after rotation?
Sir, it should be like, in a minute.
Yes, let us just try to rotate. Let me help you. Rajadeep, you're muted.
Yes, sir. Yes.
Yes. Were you telling anything?
No, sir.
Yeah. Sorry, I was asking you only, right?
Yes, sir.
Yes. Okay. Yes. So we'll do it together. It's very easy. Let's see. So we are rotating. So 2 will come down and 4 will go up. It's like 4 is pushing 2 and 2 can only come down. So 4 is at the top.
Yes, sir. So, sir, 4 and then 2.
2, correct.
And then its left one is 1.
Very good.
And the right is 3.
Very good. Excellent.
And at the right subtree it's 5 and then 6.
6. Very good. Thank you. Sorry. How many hand raised? Only 10 hands raised. How is Akhtar? I don't understand. Are you joining and leaving? Divyanshu said. Please keep your hands up. And TS, please note down the names whose hands are not up. Note down the names whose hands are not up. If you are present, please keep your hands up. And TS, please note down the names whose hands are not up. And at the end of the class, send me the list of those names. Okay, so let's continue. Let's insert 7. The first place where I have a violation is 5. And I again do right to left rotation. And so the tree look like 4 is as it is. The left part is as it is. I do a right to left rotation with respect to 5. So 6 comes above. 5, 7. Okay. So is this sort of clear? Let's continue. Let's see. Let's continue for some more time. Let's insert 15. So if I insert 15, it should be the right child of 7. Let's insert 14. If I insert 14, it will be the left child of 15. Okay. Bhushan Nakade. Bhushan Nakade. Bhushan, can you hear me? Navam Singla.
Yes, sir.
Can you tell me where is the violation after inserting 14?
At 7, sir.
At 7, very good. How should I fix it?
Rotate left.
Rotate left, very good. Can you help me? How should I rotate left?
Yes, sir. We will move 15 upwards.
Yes, just hold on a second. Let me draw the rest of the tree. 4, 2, 1, 3, 6, 5. Yes, we should do 15 upwards. And then continue.
7 at the left.
7 at the left.
Then 14 at the right.
14 at the right of?
7.
Okay, but does this fix the... yes, thank you, Navam. Please mute.
Okay, sir.
So, but does this fix the problem at 15? Does it fix the problem at this node? At this node, at this level, there was a problem, right? Imbalance thing. Balance was there. Does it fix the imbalance? The problem remains, right? Everyone can see the problem remains. We have done a rotation, but the problem has remained. What this shows is that this rotation is not enough. So So what is the message? What is the important thing? So left rotation, as we have seen, it's not that it is completely useless. This rotation is not completely useless. It was perfectly doing its job till this time, where now we are in a situation where this is failing. It is failing to restore the balance condition. Okay, so is everyone convinced that in the current situation, the left rotation has failed to restore the balance property? It was working before, but now in this particular situation it is failing. So single rotation. So here is the thing: when does single rotation fail? This is called single rotation because we are rotating only once. There is something called double rotation, and we are analyzing what is the case where single rotation fails, and those will be exactly the case where double rotation is needed, and we will do double rotation. And please, means you can be rest assured there is no triple rotation or quadruple rotation, and that's it. These are the only two cases. There is some set of cases where single rotation works. In the other cases, single rotation does not work, and where single rotation does not work, double rotation work. What is double rotation? I'll explain it, but let's first write where does single rotation does not work. Single rotation fails if left heavy followed by right heavy, or right heavy followed by left heavy. What do I mean by that? You know, at 7, look at this example. At 7, there was a violation, and the violation means what? Violation means that one subtree, the depth is more than, at least 2 more than the other subtree. But let's ask, which subtree was heavier? At 7, the right subtree was heavier than the left subtree. At the violated node, the right subtree was heavier. Now you ask, the right subtree, the root of the right subtree, at that thing, is it a balanced tree? If it is balanced, then single rotation will be fine. If it is not balanced, you ask which one is heavier in the child of the violated node, and you see that the left one is heavier. If this is this sort, like first at the violated node, left subtree is heavier, but in the left child, right subtree is heavier. Or in this case, at the violated node, right subtree is heavier, and at the right child, left subtree is heavier. If we are in such a situation, then single rotation will fail to restore balance. Now you go back here. Here you see here at 5, there was a violation, and you see which one is heavier? The right is heavier. And in the right child, which one is heavier? The right is heavier. It was right. All the cases when the left single rotation works, it should be the left heavy followed by left heavy, or it is like right heavy followed by right heavy. So when it does not work, it must be the case that we have left heavy followed by right heavy, or right heavy followed by left heavy. And as now it is clear that only these are the two cases. And if we are in this case, then we need to do double rotation. So what is double rotation? Let me define double rotation. So K3, K1, K2. I am defining double rotation with respect to K2, sorry, K3, and that rotation is left to right. Rotation is always either single rotation or double rotation. This from heavy part to the lighter part. The rotation is meant to shift from part to lighter part, and that's what we should be doing to make the tree balanced. So this is what we do: double rotation K2. K3, K1, right? Give some name A, B, C, D. A was left child of K was child of K1. Continues to do so. Yes, there was some network issue. So two slots are empty. The right child of K3 and the left child of K1. The two subtrees are should be placed, B and C, and they're only unique place. For example, where can B be placed? So B. So for C, there is no other option. C must be placed in the right subtree of K2 because C is the values in C is more than K2. So if C takes this place, B can take only this place. Okay, this is what is called double rotation, and let us apply double rotation to this case. Yes, here we are. And fix this case. Duplicate. So we apply a double rotation, and what we get double rotation at 7, and right to left double rotation. 4, 1, 3, 6, 5. Now 14 should come here. That's what double rotation does, like this. And then 7 will be here and 15 will be here. Again, observe that like single rotation, double rotation is again updating few pointers. The parent pointer of K3 should be updated. The right child of K3 should be updated. The left child of K1 should be updated, but it's the updation of few pointers, constantly many pointers. So double rotation can also be executed in order one time. It takes order one time for double rotation. Okay. So that's it. So I leave the deletion to you. It's again the same thing. You delete it, and from the deleted node, you visit that path. But for deletion, it can happen that you need to adjust. You need to adjust violations at multiple nodes. For insertion, it can never happen that you fix a violation at a node and there is still some violation in some node in higher up the tree. But for deletion, it can happen. So you need to traverse the entire path. What is the time complexity of insertion? The first step of plain old binary search tree insertion takes order log n time because we are inserting in an AVL tree whose depth is order log n, and then what is the algorithm? Then the algorithm is that after inserting in a leaf node, insertion always happens at the leaf node. You traverse the leaf to root path, and there if you find a violation somewhere, you do a appropriate rotation, either single rotation or double rotation, and that's it. So length of the traverse path is also order log n. And if you need to do a double rotation or single rotation, that also takes order 1 time. So overall, the time complexity is order log n. Of insertion is order log n. Same with deletion. In deletion, you may need to fix the imbalance at various nodes, but all those nodes will be along the path itself. And each rotation takes order 1 time, so it is order log n. Question. Where is an implementation details? How will you quickly check whether there is an imbalance or not? You can store a depth, depth of the tree at a node. For example, at every node, along with storing data and left and right pointers, and if you want a parent pointer, you also store the depth of the tree. But the depth of the tree is sort of overkill because you just need to check imbalance. So you can store some variable which can take values like 0, +1, and -1, something like that. These values are efficient, are enough, because these values are only what matters. Or maybe from -2 to +2, because it can't go more than 2 or can't go less than -2. If it is already 2 or -2, we need to do some rotation or something, so to make it 1 or -1. So you store this extra satellite information at every node, so that you do not need to compute depth of the subtree every time you want to check the balance property. Okay, so that's how the AVL tree is. Yes.
So the 0, 1, and 2, they're the depth of the subtree of the node.
No, the depth can be much higher. So one option is that you store the depth. It can be 100, 200, 500 also. Another option is that you store the difference of depth of left subtree minus depth of right subtree. This much information you store. That can be only 0, 1, or -1. Or if it is a violation, it can be at most 2 or -2. So you can store that in 8 byte or smallest possible storage space. You can store that. That is not much storage effort. But the main challenge of this sort of balanced binary search trees comes from implementation. You see that it is not understanding single rotation, double rotation is not so difficult. If I give you more examples, you can easily insert and do single rotation and double rotation. Any programmer who has experience in coding know it is how non-trivial is to handle pointers. And now if you look at what is single rotation and double rotation, it is sort of manipulating or updating pointers, and there is a lot of scope for making bugs here. So the programming laboratory, the laboratory assignment which will deal this corresponding part will be really challenging, which will really test your pointer skill. Okay, so that's it for today. So if you have any question, you can ask, otherwise you can leave. So we'll meet on Thursday for a tutorial on BST and AVL trees. Next week, we will not have any class. We will have our second class test next Tuesday from 10 a.m. The class test may be slightly lengthier, so all you need to do is to have more sheets, maybe around 15 sheets. If you keep, that will be enough. That will be more than sufficient. 15 A4 size sheets, A4 sheets if you keep. Okay. So, so that's it from today. If you do not have any question, you can leave. If you have any question, please ask, unmute and ask.